motion for a manipulator are something like this. We've done this before. MQ Q double dot plus CQ Q dot times Q dot plus G of Q equals, I'm going to write B of Q times U. I'll say why I'm writing that. Um, so this is the mass matrix, Coriolis, gravity, and this is actually a selection matrix. What I mean by selection matrix is when you have a system U, not all the controls are available. Sometimes some controls are not available. That will help us do that. Usually BQ is taken to be identity, in which case you have n joints, n motors. But here we'll assume that we don't really have n motors. So the other thing is that the system state is n cross 1. So all of this will be n cross 1. But the controls are going to be m cross 1. So B has to be n cross m. This will be n cross 1. This whole thing will be n cross 1. This will be n cross n. This will be n cross 1. This whole thing will be n cross 1. This whole thing, n cross n. So there are n states, m controls, and this matrix BQ is the control selection matrix. And we'll get to an example where you will see how what B of Q is. It just depends on the system, how many actuators are available. Okay, now the problem is this system looks very complicated, right? What we want is, we want to write it as x dot equals f of x u. So how do we do that? Well, what we'll do is we'll define, remember x is the state space and q is the degrees of freedom. So what we'll do is we'll choose x to be q and q dot. That is the position and velocity. So if you want to write the state space equation x dot, that will be q dot, q double dot. This actually is, so q dot is written as q dot, and then q double dot, I will borrow this equation here to write q double dot. So from this equation, we'll write an expression for q double dot, which is, this is q double dot. I need to write this q double dot. And so it just involves moving all C, G on the other side and then take the inverse for M. So this will be MQ inverse times, what do we have? BQ U minus CQ Q dot times Q dot plus, sorry, minus G of Q. That's it. Okay, so we've written down X. Okay, and so this is going to be our F, this whole thing, F of X, comma U. Okay, so you need to basically move this Q and make it in terms of X, but we can do that by defining, I don't know, X1 equals Q and X2 equals Q dot. I'll not write it that way. Let me just deal it with this. It's much easier to do it this way. So once we have this, now we need to go about linearizing. We have already identified F. So let's linearize. So linearization, where we have F of XU is Q dot, it's going to take a lot of space, comma U is Q dot M inverse Q bu minus cq q dot minus g q. Okay, now the first thing is a. You know that's df dx. Okay, but the state is q and q dot, right? If we go back here, the state is x q dot. So what we'll do is write same way dq. We take q dot and then try to write in terms of derivative of everything in x. And then we have dq of this whole thing. Maybe I should just write it down. Take a space. Okay, so we have, I'm going to skip the what is inside this bracket just for to make it short. C q dot minus g, and then d dq dot m inverse bu minus c minus g. Because dq dot with respect to q is 0. So this is 0. If you take the derivative of q dot with respect to q dot, that, well, it will be 1, but remember q is a vector. It has n elements. So this will actually come out to be the identity. Okay, and then there is these two terms which we'll sort of talk in detail. Let's call this 1 and let's call this 2. So let's try to simplify expressions for 1 and 2. So let's take 1 first. So for 1, we have d dq of m inverse. Well, m is a function of q, so I'll just write mq. B, say qu minus c q dot minus g of q. Okay, so we are now set to take the derivative. Now there are two terms. There is an m term, and then there's this whole thing under the bracket. So we have sort of a times b, and when we take the derivative with respect to q, we are supposed to do the chain rule. So let's apply the chain rule. First, we'll keep the second term constant, and then take the derivative with respect to the first term with respect to dq, and then this term will remain as is. And then we'll keep the first term constant. That would be m inverse of q, and then take the derivative of, what a u here, dp dq u minus dc dq this q dot. Well, the q dot doesn't really is a constant, right? Because q, we're taking derivative with respect to q. And then dg dq dot. Now g is a function of q. Now we can do a little bit of simplification here. So here we do the following. This term, what is this? This is basically, if you look at this expression for the equations of motion, what we had done is we had moved this, this, and this to the right-hand side. So it's basically this term, mq q dot. So this first part is m q q double dot. Now what we're going to do is assume that the whole manipulator is in steady state. When something is in steady state, acceleration is 0. So q double dot is 0, steady state. Okay, so that makes the life easy now, because if this whole term is 0, then we don't have to deal with this really ugly term. It's basically the inverse of m, and then you take the derivative. So it makes the life easy. So the first term drops out, it's 0. For the second term, uh, let's see. So c, so dB dq is not 0. It doesn't have to be 0. dc dq is not 0 because c is basically a Coriolis term. It will have positions, velocity, so it's not 0. But gravity term is actually only a function of the positions, not of the velocity. So this term will drop out. Okay, so we have sort of a major simplification here. This is nothing but m inverse q dB dq times u minus dc dq times q dot. Okay, so that takes care of the expression 1. Let's try to simplify expression 2. The only difference between 1 and 2 is that now we have q dot here versus q here. So let's just take that, try to take the derivative. So this second term is d dq dot m inverse v of q times u minus cq q dot times q dot minus gq. That's it. Wait, did I do a mistake here? This is not right. This is q. This will not drop out. dg dq. My bad. Yeah, that is not equal to 0. Okay, so that's that. Okay, now we have this expression. Let's take the derivative. So again, use the chain rule. We have two terms here. This is the first term. This is the second term. So first we take the derivative of m. By the way, m, I should write it as a function of q. M q inverse. Let's get some space here. Okay, so first dm q inverse dq dot, and then we just keep it as is. And then we take the derivative of the second term, so keep the first term as is. dbq dq dot u minus dc dq dot q dot minus dg dq dot function of q. Okay, now let's see if we can simplify this a little bit further. Yes, so first you notice that this term is definitely 0 because m is a function of q and we're taking the derivative with respect to the velocity. It also happens that this is 0, so it really doesn't matter which is 0, but one of them is 0 and the whole thing is 0. And now we can do some simplification here. This p is a function of q, but you're taking the derivative with respect to q dot, so this is 0. And then this term is also 0 because g is a function of q, and we are taking derivative with respect to q dot. So we're left with mq inverse minus dc dq dot times q dot. Okay, so that just takes care of one part of the linearization. We only have looked at A. A is df dx, but we also need to linearize with respect to the control. So that's the next part. So let's do compute B. That's going to be df du. What's f? F is, again, the same thing I written down earlier. F is right here. It's q dot for the first row, first column, and second row, first column. So let's write this as d du of q dot, and then d du of m inverse pqu minus cq. I'm just going to write as cq dot minus g. Okay, so the good news is a lot of things which will go to 0. This is clearly 0 because you're taking the derivative of q dot with respect to u. When you use the chain rule, this is actually a function of q. So you don't really need to do the chain rule here. You don't have to take the derivative with respect to m. So it's only this part which really contributes. So the derivative of bq times u with respect to u is b of q. So this term simplifies to simply m inverse. So mq inverse times b of q. That's it. Everything else, to see this derivative with respect to q will be 0. So in other words, b is just that. So let me summarize what we found now for a and b. So this is b, and a was a little bit more complicated. A was this, but then 1 and 2 we simplified a little bit uh, outside. So let's me write the final linearization. Okay, here's the summary. So we were after x dot equals ax plus bu. Here a is 0 m inverse minus dc dq times q dot minus dg dq minus plus, sorry, db dq times u. Here there was an identity, and then this was m inverse minus dc dq dot q dot. And then b is simply 0 and m inverse b. Okay, so there's an ambiguity here. This is b of q. I have a b here and there's a b here, but let's just call this b of q. So that's it. So if you're given a manipulated system, you could do this. So I'll give you a problem, the last homework, where you will apply this and get it super easily. You don't have to really go through the process of deriving it from scratch. Just use the formula. Okay. Okay, so let's look at an example of where we might use this. There are two examples which I will show you with code. The first example is, well, it's both are going to be double pendulum examples, and you might have seen videos of these examples. So if we have a, a two-link manipulator, so Q1 is the first joint, Q2 is the second joint. Okay, so what's different is the following. In one case, I have a single actuator, and that applies a torque U1 at the shoulder joint as shown U1. The second one, again, there's a single actuator which applies a single torque at U2. So one actuator at Q1, one actuator at Q2. Now, the thing about these problems, specifically when you have two joints and only one actuator, these types of systems are called underactuated system. Okay, you do not have control over both joints. This makes control really hard. Okay, imagine that you have a hand and your muscles don't really work on the elbow joint. You cannot really control the elbow joint directly. So controlling this is really hard. So what we'll do is we'll look at how do you balance these systems in upright position when you hit with a stick or perturb the system. Okay, so this robot on the left side, and if you can go to Google and search for it, it's called a Pendubot. It's a very classical control problem, and they have made systems like this and use this for maybe a controls class to show that it works. You can control the system. And this one is called the Acrobot. Acrobot. Now, this Acrobot is because when you have an acrobat, like the Olympics say, you can only apply torque on the hips, right? So that's, if you think of this as a person, with this is his hand and this is his hips, so there's a actuate the hip, that is your hip joint, and so you can only use that, and that's why it's called Acrobat. Okay, so what we need to do is, our goal here for both these systems, stabilize about the vertical position. Okay, that's our goal. So it's going to be upright. Then you hit it with a stick or perturb it, it should stabilize. So what we'll do is, this is how we'll do it. First, we'll get the equations of motion. Okay, so mq q double dot minus plus c q dot plus gq equals pu. Second, we'll linearize to get x dot equals ax plus pu, where x will be q dot. Third step will be use LQR. Okay, so we'll try to come up with a controller which looks like this by using the command LQR. What does this look like? Well, it'll just be u either I'll call that I equals 1 or 2, depending on which joint it is. It's going to be something like this: K1, K2, K3, K4, Q1, Q2, Q1 dot, Q2 dot. So in order to control the system, I would need, this is a feedback controller, by the way, because you need a sensor to measure the angles of the joints, Q1, Q2, and the velocities of the joint. You could take the positions and differentiate, or take the finite difference to find the velocity. That's what is usually done. But once you have the sensor value, capital F, uppercase X, and you have gains, which comes from LQR, these come from LQR, you can apply this controller and control the system. Okay, so here is how you do it. Okay, the first step is to derive the equations, and this is not new. We have derived the equations for a double pendulum for some time now. This basically uses the homogeneous matrix to figure out, first of all, the positions, velocities. That is, I'm using the Lagrangian. So L is t minus v. I got the Lagrangian. I derived the equations using the Euler-Lagrange equations. I got the equations. That's the first step that we have done. Now, this code does something more than that. It actually gives you the Jacobians, the things which we care about in the A matrix, A and B matrix. So here is it producing dg dq, dg dq dot, dc dq, dc dq dot. This is actually as simple as just doing g times Jacobi. So take the g and take the Jacobian with respect to Q, the angles, and take the Jacobian with respect to Q dot and so on. So once you get that, it prints out all the various derivatives. Now, once you get this, you run this code, and it might take some time. It produces the result in the output or the terminal over here. You need to take this and copy paste in the second part of the code, which I'll show you. Now, you could automate this, but I just chose to do it this way. So this is basically giving the terms in the Jacobian. You need to match it with what equations I have. Then go to tooling LQR and paste it at some places. So for example, I need the equations of motion, which would feature, well, in this case, this is called linearization. It basically writes the linear equation. So getting A and B. So all these are the inputs, but what comes out of this is A linearized, B linearized. So A lin, B lin. So the same as above. I wrote B lin and A lin because I have an ambiguity here. I actually have B of Q as an input, which happens to be the term in front of U. So this code actually can do both Pendubot and Acrobot, because if you go up here, you can see if you want Pendubot, just put B as this. If you want Acrobot, put that. So let me run this first. So it computes the LQR gain, and then I think I put some kind of a torque disturbance, so it has to stabilize. So it's here, I'm just perturbing it, and so it stabilizes itself. So you can sort of barely see it, but it's perturbed. So the way I perturb the system is, this is just showing. So if I don't perturb it, it will not really do much. It's not very interesting because it's all standing straight. U will be 0, right? Because the deviation is 0. Here what I do is I have some control over how I perturb the system. These are the ways I can perturb. I could put a torque disturbance. I could put a theta disturbance, theta dot disturbance. So in this case, I chose the velocity to be, there's some random noise given to the velocity. And that's why when you feedback, you're not feedback perfect information. So you can put that 0. And then if you wanted to have like an unbalanced torque, so let's put, so when you supply a torque, what this is doing is supplying a counter torque, which is standard deviation of 40, and then it's random normal distribution. So this may or may not work. If it's too much, it's probably not going to work. But you could try various combinations. So I think it failed. Yeah, that's a sign it failed. Yeah, so it will go unstable. So this is clearly, the system will not be able to stabilize itself if you give large perturbations, clearly, because the main fundamental issue is that the A and B matrix are true only for a very small neighborhood at the 0 position. So it's normal, it's linearized about 0, 0, 0 for the position, 0 for the velocity. So if you hit it and the velocity changes by a substantial amount, then it's not going to come back because the linearization doesn't hold true. So it just goes unstable. But if you try a small value, it may work. No, again, no guarantees. Let's try 10 instead of 40. So for 10, yeah, it's just string. And it looks much more interesting, I guess, if you put velocity disturbance. So that's that. Let's do it the other way, which is, let's go here and then change this from this system, the Pendubot, to the Acrobot. Okay, and what works for the Pendubot may not work for the Acrobot. So let's run this. So Acrobot has no, this failed actually. You can see it's failed. It's going to do something crazy. So for an Acrobot, it's much, much harder to stabilize. Yeah, so that's that. But you can try various things here. So what I've done here is essentially, and of course, you could also tune the LQR controller. I should have it somewhere embedded here. There is, so I chose my LQR controller to be just Q is just identity, and R is 1e negative 2. Okay, now if you want a very reactive controller, very strong control, then you want to reduce this. You could even go like -5. This will increase the gain substantially because it will cause, when the R is, remember the R comes in front of the u square. So it's basically r times u square. So the smaller the r, the bigger u will be applied, u being the torque. And so if you run this, now it's going to be very, very aggressive in terms of stabilizing. So we could try this and see if it works. There's a good chance it will not work, but we can try Acrobot with this new controller. It didn't work. That's too much. The disturbance was too much. Okay. Let me stop this and just try it with Pendubot with a more aggressive control and see what happens. I've changed the R to 1e-5. You see, it's not at all deviating because the control is so aggressive that it doesn't let it move. Now, if you change this back, so you saw that it started at a very a different angle and then it stabilized, but it's not moving. But as you make it smaller and larger and larger, you don't recruit the torques as much, and then it just doesn't. It is not very aggressive. So let's see where do I have the R? Here it is. Okay, here is 1, which is even larger than the 1e-2. So it's going to be doing that because it's not very aggressive.